Hi, my name is Sefi and I'm the VP of AI at Deci. And today I want to talk to you about the AI production barrier and how to solve it. It's no secret that deep learning is powering the next generation of computing, from conversational computations to autonomous driving, all the way to placing a pig's nose on my face when I'm uploading a TikTok video. What's surprising is the algorithmic complexity is growing exponentially. In the NLP domain, within a year, models have gotten bigger by a factor of 1,000. And it's not only in NLP, also in vision, we see a similar phenomena where in order to get better accuracy on ImageNet, models are getting bigger and bigger. We even see a model that has over 100 million parameters simply to get 82% accuracy on ImageNet. Now, this is unacceptable for models to get bigger and bigger when hardwares are getting smaller and smaller and we're running deep learning models on our mobile phones or even on watches. In order to address this problem, an important paper called EfficientNet came out, where in EfficientNet, they ran an algorithm called NAS, a neural architecture search. It's in fact letting the computer find the best architecture that optimizes a specific goal. In this example, the algorithmic complexity. So now we see models that both have a high accuracy, but with a low algorithmic complexity. So in fact, we might think we've gotten what we want. But the bad news is that algorithmic complexity does not always relate to performance. In fact, it does not often relate to performance. For example, if we check the performance on this chip, on the NVIDIA Jetson Xavier chip used a lot for inference of deep learning, and if we pick 3 models out of this plot, we see that the algorithmic complexity does not relate to performance. In fact, the fastest model out of these 3 is ranked second in terms of the algorithmic complexity, in terms of the gigaflops, and actually counterintuitively has the largest number of parameters from these 3. And this gets more complicated when we go and check all the hardwares we're running deep learning on, from cloud to edge to mobile phones. And the bad news is we must check for each and every one of these hardwares the performance of each and every one of these models. Otherwise, we're getting suboptimal results. The good news is that that's exactly what we do at Deci. We offer a deep learning acceleration platform, a SaaS platform that allows you to benchmark models on various hardwares within a click of a button, allowing you to select the best performing model. We even take it a step forward and optimize a model for each and every one of the use cases. We develop what we call the AutoNAC engine. It's an automatic neural architecture construction engine. It takes as input your task, your data, and your inference hardware, and it runs an optimization engine. This engine outputs a model, a custom-made model that has the best performance for your use case. If you change one of the components in the input, you'll get a different model in the output. And by that, you can achieve the best performance for your use case. So let's take a look at some results. In this example, we have the accuracy on the y-axis and the latency on the x-axis. Note that now the x-axis is in fact the performance we're looking for. This was benchmarked on the ImageNet dataset on a T4 GPU, a very common and well-known benchmark that a lot of these models were optimized for. You can see the state-of-the-art models here from MobileNet through ResNet family, all the way to EfficientNet we've just discussed, performing very well on the T4 GPU. But if you optimize a model using Deci's AutoNAC for this specific use case, you'll get the best performing models you can get. And if we take a step away from this common benchmark and just change the hardware to the NVIDIA Jetson Xavier, now we see the same models benchmarked on this plot, but now the boost you can get using Deci's AutoNAC is much larger. And let's even take a step farther away from the common benchmark and check what happens with object detection on Coco on an iPhone, which was published less than a year ago, the iPhone 12 Pro. You see on the y-axis the accuracy for object detection, and the x-axis the throughput, how many images can it analyze per second. YOLO v5 is what is known these days as state-of-the-art object detection, and SSD Lite is also one of the state-of-the-art models. When you apply Deci's AutoNAC to get a custom-made model, this is the performance you get. You get a 3 to 5x acceleration on top of the state-of-the-art, allowing you to analyze more than 200 frames per second on a simple or not so simple iPhone 12 Pro. So let's take a look what happens to customers we apply Deci's AutoNAC to on various hardwares and various tasks that obviously it is hard to find a model that optimized for this specific use case, but Deci's AutoNAC allows to do that. And by optimizing for each and every one of the use cases, this is now the performance you get. Between 2.4 to 12.8 acceleration on top of the optimized model that was done by the company running these models in production. So the takeaway from this is rather than taking a model off the shelf, a FisherNet or ResNet or MobileNet, and applying it for your use case, do it the other way around. Take your use case and apply and find a model for that specific one. And that is exactly what we do at Deci. We find the best neural network for the task, data, and inference hardware. Thank you very much. I welcome you all to sign up for our community and run Deci's platform tomorrow.